Hi, to understand about stresses, we must know what loads are. In any engineering system, components are subjected to external forces. These external forces are called as loads. Loads can be of many types. For example, axial load. An axial load is a load that acts along the axis of the component. Consider this body. The load P is an axial load because it is acting along the axis of the body, which is the longitudinal axis. Bending load. A bending load is a load that bends the body. Consider this body, which is fixed from one end. A load P is applied on the body. Due to this load P, the body will bend in this manner. Therefore, this load P is called as a bending load. There can be other types of load like torsional load that we are going to study later. Now, if a component is in equilibrium, net load on the component is 0. Consider this body which is subjected to axial loads. The net load on the body is P minus P is equal to 0. So if net load on the body is 0, then why study these loads? The answer is simple. These loads tend to develop an internal force in the system. This internal force system can deform the body and may even break the body. To understand internal force system, consider a bar on which axial tensile load is applied. To understand about internal force system, make an imaginary cut in this bar as shown that divides the body into two parts A and B. Now the entire body is in equilibrium because the load on the entire body is P minus P equal to 0. Therefore, the part A of the body or part B of the body must also be in equilibrium. Now consider part A. Part A must be in equilibrium. Therefore, to keep this part A in equilibrium, an internal force F must come from part B. This F is called as internal force. Now this internal force F is acting at the center. We have learned that if a force is acting at the center, then this force is equivalent to a uniform distribution of force. So this force F is equivalent to a uniform distribution F1, F2, F3 and so on, F2, Fm. And all these loads F1, F2, F3, all these loads must be equal. If the internal force is uniformly distributed on the area, then we can write normal stress or direct stress as internal resisting force divided by the area of cross section. So if the distribution is uniform, then you can directly write normal stress as total internal force divided by the total area. Therefore, we get the units of normal stress as Newton per meter square, which is also called as Pascal. However, if the internal force is non-uniformly distributed, for example, as you can see on this body, then in this case, to calculate the value of stress, you need to first choose a differential area. Take this differential area. Let the differential force on this area be dF. Therefore, we define stress as the differential force acting on the differential area. In this case, if you directly write total force upon total area, then you get average stress, and average stress is not equal to stresses at different points. For example, the stress at this point may be sigma 1, stress at this point may be sigma 2, stress at this point may be sigma 3, stress at this point may be sigma 4. All these stress have different magnitude because the internal force is non-uniformly distributed. However, if the internal force is uniformly distributed, as we have seen in case 1, then in this case average stress is equal to stresses at all the points. All the stresses are equal to sigma. Therefore, to write the stress, we need to first consider whether the internal force is uniformly distributed on the cross section or it is non-uniformly distributed on the cross section. If the distribution is uniform on the cross section, you can directly write stress as total force upon total area. If the distribution of internal force is non-uniform on the cross section, then you need to consider a differential area, and stress on that area can be written as differential force acting on that area divided by that differential area, as we have seen here. Differential force on this differential area, then the stress is dF by dA, and the average in this case can be written as total force upon total area. The normal stress can be tensile or compressive depending on the nature of load. A tensile normal stress is that pulls the surfaces apart. As you can see, these two stresses are trying to pull the surface apart in this manner. And a compressive normal stress is that tries to push in the surfaces. These two normal stresses are trying to push in the surfaces, as it can be seen. We are going to take tensile normal stresses as positive and compressive normal stresses as negative. Now, shear stresses. To understand shear stresses, we need to know what is a shear force. A shear force is a force that acts parallel to a surface. That is, it is a tangential force. For example, this force is acting parallel to this surface. Therefore, with respect to this surface, the force P is a shear force. In two dimensions, this block can be drawn as this. To find shear stress, make an imaginary cut in this block. There will be an internal force V on either parts A and B. The shear stress can be written as internal resisting force by area on which shear force is acting. The area that you need to consider is this shaded area. Now, the sign of shear stress depends on the sign of area on which shear stress is acting. Therefore, to understand the sign of shear stress, we must first understand the sign of area on which shear stress is acting. So, area is said to be positive if its outward normal is in positive direction. Consider this area. This area has two normals. One inward normal points inside the body and one outward normal that points outside the body. To find the sign of the area, we need to consider the sign of only outward normal. To consider the sign of outward normal, first draw coordinate system. Let the coordinate system be like this. As you can see, this outward normal is pointing in the positive direction of x-axis. Therefore, we will call this shaded area as a positive area. So, let's come back to the sign of shear stress. A shear stress is positive if it acts in positive direction on positive area. To understand this, consider this shaded area. Let the coordinate system be like this. The outward normal of this shaded area is in this direction, which is in positive direction. Therefore, this shaded area is positive. So, on this positive area, if you see the direction of shear stress, it is acting in plus y. Therefore, we call this shear stress as positive shear stress, because a shear stress is positive if it is acting in positive direction on positive area. Take another example. Consider this top area. The outward normal of this area in this direction. You can see this is a positive y direction. Therefore, we call this area as a positive area. On this positive area, shear stress is acting towards right, which is actually the positive x-axis. Therefore, this shear stress is acting in positive direction of axis on positive area. So, again this shear stress is a positive shear stress. Take another example. Again consider this area. This area has a outward normal in positive y direction. So, we call this area as the positive area. On this positive area, the shear stress is acting towards the left, which is actually the minus x direction. So, this shear stress is acting in negative direction on positive area. So we call this shear stress as negative shear stress. This ends this module.